I want to spend a little time talking about the history of quantum mechanics, and this is going to be kind of a brief history because I'm going to try to keep this short-ish. But quantum mechanics is really the study of the wave or energy behavior of particles. So particles have mass, they occupy some sort of volume, but they also are themselves energy. And the smaller the particle, the more this energy or wave nature plays a role. So things like electrons, if we're talking about teeny tiny particles that are important in atoms, electrons also have this kind of wave and particle duality. That's one way. It's kind of a simplified way of thinking about it, that they act as particles, they act as waves. We can talk about the energy of them because they are energy, they have a wave nature, and they have mass. So a quantum is a discrete packet of energy, and a quantum you could kind of think about as a particle of energy, which the language is tricky and quantum mechanics is wacky because you can't really have a packet. It's not like you have a little satchel full of energy and there's your quantum, but that's sort of the way we picture it. So we talk about a quantum, like for light, for example, is a photon. That's a discrete packet of light energy. The plural for this, by the way, is quanta. So you'll see it both ways. Quantum is singular, quanta is plural. And so where did all of this start? Because it's just kind of a wacky way to think about matter, and our understanding of this comes about in very theoretical contexts that are experimentally determined also. So they came from actual experimentation. These experiments gave us an insight into the wave nature of particles and of matter. And it kind of started with scientists such as Max Planck. I've heard Max Planck's name as Planck and Planck. I like Planck personally. I don't know German, so apologies if I am mispronouncing it. So Max Planck, because then the funny thing is we'll talk about Planck's constant. So I always say Planck's constant, but Max Planck. So it's a grab bag of language, linguistic grab bag. Okay, so he was studying solids. So he's a German physicist. I like to, claim all of the physicists as chemists, but he really is a physicist, and he was looking at the intensity of light, which we measure in lumens, so light intensity, that's emitted from a solid that's raised to different temperatures. So a solid is raised, so we're increasing temperatures of solids, and if you do it to a specific temperature, then there will be light that's emitted. So if you've ever seen something glow red hot, then that's what you're seeing. You're seeing something heated up to the point where the solid particles within that are vibrating, and these vibrational frequencies put out light at a specific wavelength, and we perceive that as red when you go up to temperatures like 750 degrees. And if you go even hotter, then the light that comes out is white. Have you ever seen something glow white hot before? That's the kind of idea. So again, solids are made up of particles that are closely packed together. Kinetic molecular theory says if we increase the temperature, then we increase the motion of these particles. Now the motion of solid particles is pretty restricted, so this motion is vibrational. And a vibrational motion is a wave, right? If you picture something vibrating, that vibrational energy we can describe with a frequency, how many oscillations we have per unit time. And Planck found that there's a relationship between the energy of these vibrations and that frequency. So remember, nu is our frequency, talking about the vibrations here. H here is Planck's constant. Told you. And Planck's constant is 6.63 times 10 to the negative 34th, and the units on that are joules times seconds, joule seconds. And then n here is a whole number that's greater than 0. So these are kind of 1, n equals 1, 2, 3, etc. And then this is my vibrational energy here. So what this means then is that we have this constant that's relating the two, and we have a simple whole number that is going to be proportional to that amount of energy. So the energy and the frequency are proportional to each other, and they're proportional in whole number ratios, which means the energy and frequency are kind of quantum phenomenon. So anytime you have this n here, which is your principal quantum number, then we have something that is proportional by simple, discrete, whole number packets. And that's kind of what we're talking about here. So the energy here is quantized, and it's quantized with relation to these packets of frequency that is coming from this vibrational energy in solids. So this was kind of an interesting and useful observation, and it led into some work that was done by a famous scientist. Perhaps you've heard of him, Albert Einstein. We usually think of Einstein, or a lot of people go to E equals mc squared, or his work with relativity or special relativity. But Einstein actually got his Nobel Prize in physics for the photoelectric effect. And the photoelectric effect is an important kind of feature for understanding the movement of electrons and in understanding kind of the way that metals work. So he had an experimental setup here. He had a source. The source shot some light onto the metal, and then at specific wavelengths, at specific packets of energy, that metal would release electrons. It would eject electrons at specific wavelengths. And of course, these electrons would be attracted to my positive pole here on my ammeter, and then so we can measure a current that comes off of this. So you hit this thing with light at specific frequencies, then we would see that there's a current. At other frequencies there weren't. So we found that there's this relationship between kind of the light energy, so this is some sort of light source, and the electron movement, so the energy of these electrons that are coming off of the metal. And so there's kind of this relationship then between the two, and Einstein related them by Planck's constant. So again, this kind of looks like the same setup where we have the energy of this thing, Planck's constant, and the frequency. So again, there's this direct relationship between energy and nu. And what he found is that there's a couple important features from all of this. There's this threshold frequency, which is the minimum nu that's required in order to eject electrons. And there's what is called the work function, which is the same thing, but in terms of energy, right? It's the minimum energy that's required to eject electrons. And both of these things are specific to materials. So these are all characteristic of whatever it is that we're talking about. So you'll have different threshold frequency and work functions for different materials, and it's the minimum either frequency or energy that's required to eject these electrons when you shine specific packets of light. And so there's this relationship here between energy and frequency, and they're related by, again, Planck's constant. So using this kind of setup and this information, we can solve problems that look like this. What is the energy of a UV photon? So we have a wavelength here. We're in the UV range. Now we can relate that wavelength to an energy. And the way that we can do that is we know that the speed of light is equal to the wavelength times the frequency. So if we solve for frequency here, that's equal to the speed of light over the wavelength. So we can plug in our speed of light, which we're going to round in this way, 3.00 times 10 to the 8 meter per second. Divide that by our wavelength. Wavelength in meters, of course, because it's a distance, it's a length. And we end up with a value of 3.00 times 10 to the 16th per seconds, or seconds to the -1 hertz. So again, if we're thinking about a frequency, that's the number of vibrations, that's the number of oscillations that we have. And now with Einstein's equation, we have a way to relate our energy to that frequency. So we're trying to solve for the energy. We know that Planck's constant is 6.63 times 10 to the -34th. Again, units on that are joule seconds. We're going to multiply that by the frequency that we just calculated, 16ths per seconds. So when we multiply these together, if we're doing some unit analysis here, we have a per second and a joule second, so the seconds will divide out and we'll be left with an energy in joules, which makes sense. And we end up with 1.99 times 10 to the negative 17th joules, which doesn't look like much, but it's one photon, right? It's a tiny amount. It's one little packet of energy with that particular wavelength. So that's the amount of energy. Now think if I have a mole of those, or if I have multiple moles of those, then this number can get pretty fast, right? Because you get 1 mole of these and we're multiplying by 6.02 times 10 to the 23rd. Now we have a positive exponent for our scientific notation. Now this also brings us to wave-particle duality, because remember that a joule is equivalent to a kilogram meter squared per second squared, right? That's what a joule is. And so what I'm saying is that I have a wave nature of this photon, right? I can talk about its frequency, I can talk about its wavelength. And when I plug this in and I talk about the energy of it, it gives me something that has mass right there in the units. So this energy implies mass, implies matter. So now I have something that is energy that also has kind of a particle behavior. So it kind of leads into this idea of wave-particle duality, which is just kind of the wackiness that is quantum mechanics. So let's talk about what this really means, kind of from an energetic standpoint. What Max Planck and Einstein were saying, as well as Niels Bohr, who's kind of wrapped up in all of this too, and working around the same time, is that energy is quantized. It comes in discrete packets. And these discrete packets are matter dependent. So depending on what the substances that we're looking at, then it's going to behave slightly differently depending on its atomic and subatomic structure. If we think about it in terms of potential energy, so let's talk about potential energy. We know that potential energy is the energy of position, and when you're calculating potential energy, it's the mass of the thing times the height of the thing times the force that's pulling on it, like gravity, for example. So if I have a human here, this is not going to be to scale. So here's a human. It's very tall steps. The human is here on the ground floor. Let's call that kind of my nucleus here. And so the human can be on this ground floor, or the human can be on this step. But the human can't be anywhere in between. I can be on step 1, or I can be on 0, or I can be on step 1, or I can be on step 3. But I can't be anywhere in between. I can't be on step like 1.5, just physically, right? There's some physical barriers to being in between these different levels, these different quanta, if you want to think about them that way. So we have these fixed positions that I can be at. So I can only have certain potential energies that are allowed. So I have a certain potential energy here. I have a certain potential energy here. But I can't get this halfway point, right? I can have the potential energy at step 2. I can have the potential energy at step 1. But I can't have step 1.5. I can never be there from a physical standpoint. There's a barrier. There's only certain allowable energy levels, and that's again dictated by the material. So that's what it means to be quantized. That's as opposed to something like, let's say I have Willy Wonka here. That's pretty good. And he's got his cane, right? That's good. And then his hat. And let's do the Gene Wilder version. So he's got the crazy hair. So here's Willy Wonka. And Willy Wonka, we know, has his glass elevator. And his glass elevator kind of looks like a rocket, right? And it can go in infinity directions. It can go upways and sideways and backways and frontways with impunity. So there's no limit to the potential energy. If we're thinking about position, if we're thinking about height, he can be anywhere in between. We have infinite possibilities for that potential energy. He's not quantized like our human here on the steps, right? We have this quantized set strata that we have to go through that's limiting our potential energy. With Willy Wonka over here, we have infinite potential energy. So this is what we mean by quantized, that there's only certain allowable values for these energies, and that we can relate them in simple whole number ratios. Kind of wacky.